Here is the honor code stating that our work is not plagiarized and is consistent with the rules described by Georgia Tech. This presentation depicts the progress made thus far in the refrigeration experiment block for ME 4056 Systems Lab. As an overview for the following presentation, Burdell Inc. was hired to review the cooling system proposed by Machine Chillers Inc. This system focuses on the use of a vortex tube for cooling purposes. The goals of the previous week's lab was to characterize the vortex tube's relationship between input pressure, denoted as P3, versus T4 cold and hot, and M dot cold and hot. The origins of these properties will be talked about in the next slide. Additionally, we want to characterize the steady state energy transfer from the input pressure of the system and the vortex tube to the load. Further into this presentation, we will be talking about the system anatomy, the various processes and assumptions made, the data that was collected thus far, and our analysis and characterization of the system. Here are the main components of the system. On the left is the lab setup, and on the right is a diagram with labeled sections. Initially, pressurized air is injected into the system at a pressure of P3 and enters the vortex tube, as seen in the diagrams. The air is then separated into hot and cold sections and pushed to either side of the system. The hot air is pushed out of the warm side of the vortex tube, denoted as T4 hot, and flows out of the system at a measured flow rate of M dot hot. For the cold side, the air exits the cool side of the vortex tube at a temperature of T4 cold and then flows into the load, thereby cooling it to a temperature of T load. Finally, the air exits the load at T5 and then the system at a measured flow rate of M dot cold. We'll briefly go over the methods used for the data collection and analysis. Shown here is the schematic of the refrigeration system. Using thermocouples, data for the temperatures was collected. The temperatures we are focusing on for this experiment is the inlet temperature, denoted as T3, T4 hot and cold, the temperature leaving the hot and cold sides of the vortex tube respectively, the temperature of the load, and the temperature leaving the load block, denoted as T5. The goal of the refrigeration system is to cool the low block, which is a block of aluminum insulated in styrofoam.
We're also interested in measuring the flow rates at both the hot and cold outlets. The flow is measured as volumetric flow in liters per minute, and from there we can convert to mass flow in kilograms per second. To verify the model, we'll experimentally determine the performance of the insulation material, which in this case is styrofoam. From there, we can compare this to the theoretical thermal resistivity, which we can calculate given the measured dimensions of the insulation and the theoretical value of the styrofoam's thermal conductivity, which is 0.033 joules per second meter Kelvin. Several assumptions are made during the analysis. Considering only steady state allows us to simplify the energy balance performed on the load block. At steady state, there should be no change in temperature of the block, so energy load equals 0. We can then observe that the energy entering the block from the surroundings, energy ambient, is equal to the energy entering the fluid between 4C and 5. We can then assume that energy air is equal to the temperature difference between T5 and T4 cold multiplied by the mass flow and specific heat of the fluid. This allows us to then characterize the ambient energy entering the block through the insulation. A few more key assumptions are made during the analysis. We can reasonably neglect radiative heat transfer between the load block and its surroundings since the material is well insulated. We also assume that the various connections of the system have negligible heat loss, though the effect of this assumption should be investigated further.
When collecting our data, we referenced our temperature outputs to determine when the system had reached steady state, and thus when to stop collecting data. The temperatures collected to reference the steady state were the temperatures of the output flow of the vortex tube, T4 hot and T4 cold, the temperature of the aluminum block, T load, and the temperature of the output flow from the block, T5. As you can see, the temperatures gradually changed as the pressure increased, eventually reaching close to a steady temperature. It was up to our discretion to decide whether the system had reached a steady state, so we decided it was when the last temperature reported was within about 2% of the previous 100 points for all temperatures recorded. This was hard to visualize without an aid, but a baseline of 1,500 counts or so to start comparing was sufficient in helping us discern the steady state temperatures. You can see here that for a nominal gauge pressure of 80 psi for the system, the steady state was recognized at about 1,600 counts, as noted by the magenta line. A few hundred points were collected afterwards to ensure that the system had reached steady state. The relationship between the output flows of the vortex generator and the absolute pressure of the system were dissimilar. The hot output flow temperature increased and the flow temperature decreased as the absolute pressure increased, as expected. The inability of the uncertainty ellipses of the York fit between the cold output temperature and the absolute pressure and the nonlinear nature of the data points suggested that a quadratic fit was a better means of relating the two. The relationship between the hot output temperature and the absolute pressure was more linear, as evidenced by the intersection of the uncertainty ellipses and the general linearity of the data points compared to that of the prior relationship. The nonlinearity between the cold temperature and absolute pressure suggests discrepancies when trying to determine the thermal conductivity of the styrofoam, since the rate of heat transfer is assumed to be linear. Regarding the mass flow outputs, both of them suggest a nonlinear fit. The York fit between the cold mass flow rate from the vortex generator and the absolute pressure does intersect the uncertainty ellipses, but the trend suggests a quadratic fit would fit better. The uncertainty ellipses do tend to increase their major axis, due to the combined uncertainty of the mass flow sensor proportionally increasing as their flow measurements increase. Despite the increased major axes, however, the York fit between the hot flow rate and the absolute pressure does not completely intersect the uncertainty ellipses, and the data points more visibly develop a quadratic trend. As with the temperature relationships with the absolute pressure of the system, the nonlinearity between both flow outputs and the absolute pressure also suggests discrepancies when trying to determine the thermal conductivity of the styrofoam, since the rate of heat transfer is assumed to be linear.
To ensure accurate results, T3 and T ambient were compared during steady state in accordance with one of our assumptions. This ensures the pressurized air leaving the accumulator is representative of ambient air, one of our assumptions. The green numbers here are those where the T3 lies within the uncertainty bounds of T ambient. Red is where it lies outside. All values are inside except for one. The discrepancies here can be from residual heating from previous experiments, some heating from the environment, from the fact that the pipes are not perfectly insulated, and also the fact that the heat exchanger and the accumulator are thermal loads that are not accounted for. On the right-hand side is a table that compares measured thermal mass with experimental thermal mass and uncertainty. All of our values are well outside of the uncertainty bounds. This could be accounting for some of the unmodeled thermal loads, but more importantly, this is the assumption to find the thermal mass is that Q ambient in the transient phase is 0, when this is not true, since there is going to be some heating to the load from the ambient air, especially at colder temperatures and at the higher PSIs, which is why the thermal mass decreases at these numbers. Next, we're comparing some experimental and theoretical conductivity values. Our experimental conductivity lies well outside our theoretical, outside the uncertainty as well for the first three, but it's trending downwards and towards theoretical value and ends up inside the uncertainty. The conductivity here decreases with pressure because the larger Q air term, there's going to be a small discrepancy between the outflow T5 and inflow T4 cold to the load. This would increase the thermal resistance and therefore decrease the thermal conductivity. We also have the heat transfer rate from the air at steady state. This generally increases with pressure. There's a slight jump at 60 psi, but the trend is there. And this can be accounted for by the increased heat transfer from the ambient air to the load when the temperatures are lower at those higher PSIs. Some sources of discrepancy. First of all, the connectors are not perfectly insulated bodies. The pipes will have some heat exchange with the environment. The linear fits, especially those for the cold temperature versus P3, are not accurate. They are taking a linear fit to data that is clearly not linear and therefore not modeling the behavior properly. The load is not perfectly insulated from the environment. There is a gap in the insulation at the top that will not be accounted for in the lumped capacitance model. Finally, the compressor and radiator are thermal loads that are not accounted for by the model. Thank you, and here's our works cited.